Hi, my name is Albert Dunford, and in this tutorial video we are going to do a boost PFC. So we're going to turn this boost converter, which is running an open loop, and we're going to turn it into a PFC with average current mode control and an outer voltage loop. We'll do it in the analog domain, and we'll also do it in the digital domain. So let's have a look at this converter working in steady state here. I've got this running in free run mode so that we can sort of look at it like it is on the test bench. So we'll start the simulation and pull up the oscilloscope here. So we can see the blue line is the output voltage. I've got it offset by 200 volts. So we've got about 200 millivolts of peak-to-peak ripple on the output voltage. We're running at 2 kilowatts. We've got 50 kHz. The input voltage is 120 volts. The output is going to be 200 volts. And then the red line here is the current. So the current, I've offset it by a little bit as well. So it's about 16, 17 amps, and we can see we've got about just over an amp of ripple on the inductor. We can play with these values, and maybe we want to reduce the ripple on the inductor a little bit. So let's push this up to say half 500 microhenries, and see what that gets us. And we can see we've reduced the ripple a little bit there as well. But in general, this looks to be an okay design for a boost. But this is not going to really cut it for a boost PFC. So I'll kind of show you what's going to happen if we were to take a PFC with these energy storage values. So we'll stop the sim here, and we'll close that. And what we'll do is we'll just quickly put on a sinusoidal input. So we'll put in a diode bridge. Okay, so we've got our boost converter set up now with a front end as a rectified signal, and we're going to feed into this 120 volts RMS. So this is the peak amplitude, so we need to multiply by √2, and so we're going to push this in, and then we're going to look to see what the ripple values look like. So I'm going to need to adjust the reference voltage, and then we're also going to be able to look to see what the ripple is on the output here. So let's switch this back to, we're still in free road, and we'll run this, and we'll have a look at the output waveforms here. So let's change this. We're going to need to increase this by quite a bit. We'll rescale this, okay, and then we'll drop the current down. So let's, okay, so we've got the waveforms triggered on, and we can see the impact now of having that sinusoidal impact. The inductor current in red now has a definite charge up period to it, and the output voltage is shifted up. We should actually reduce the reference here, probably in half to get it down to 200 volts, maybe a little bit more, 2.5. So there we are, back sort of centered around 200 volts, but the key point about that is that I'm on 100 volts per division here, so we're looking at a ripple here of close to 200 volts. So the energy storage values that we had with just a straight boost converter don't really apply anymore. We need to really add a lot more bulk capacitance on the output in order to mitigate this ripple voltage here. So we're storing enough energy. So this will be, we'll need to increase by quite a bit. So let's go up to like 1 millifarad and see what we get with that. And we'll zoom in again. Maybe I'll reduce this down a little bit as well. Okay, so now we're on 20 volts peak to peak, or 20 volts per division, and so we're still getting close to 50 volts, 20, 40, and then almost 60 volts. But this value is going to be pretty good for us. Once we close the loop with average current mode, we'll see that this ripple is probably going to be halved. We could add a little bit more bulk capacitance on, but I think a 20 volt ripple on the output will probably be okay, and we'll go from there. So we'll use these values now as our for our converter. So what we need to do now is we'll turn the AC source off. We'll convert back to DC, and we need to set up an AC sweep here. Now before I do the sweep, let me turn off the free run mode. I'm going to, we'll do a digital implementation of this as well, so I'll just copy and paste this and disable it. We'll get back to that when we do the digital sweep. So we'll insert a perturbation here, and we need a sinusoidal source. We'll ground it, and then we need to grab the AC elements, so the multi-sign sweep block, and we'll grab the AC probe as well. We'll stick that on there. So this is going to be IL and log, and we need to set this block up. So what we need to do is understand where steady state is. So we'll run this, and yeah, so there's right on 200 volts now. And yeah, things look pretty stable by 200 milliseconds. So what we'll do is in this AC sweep block, so we'll put 200 milliseconds in, and we're going to sweep the source Vsin 1, which is this guy here, so Vsin 1. And then we'll sweep from a relatively low frequency, probably close to, say, 10 hertz, and we'll go up to just before switching over to 20k hertz. And then this reference amplitude here, this needs to be between 5 and 10% of the reference. So if we're 0.4, then 0.04 would be what we want. But I already know that there's going to be a lot of resonance in the circuit, so we'll start at 5%. So we'll start down there at 0.02. And now after we enable this block, we're ready to run. So this simulation will sweep through from 10 hertz to 20k. And we're going to get a nice looking, hopefully a nice looking bow plot on the output here. So that's what we see here. Now, we could sweep a little lower as well, and maybe I'll do that in another sweep here. So I'll redo this simulation with a lower sweep, but we'll come back to the video right away here. Okay, so here's the sweep with a much lower frequency of 1 hertz as the start. It took 28 seconds to run, but we'll save this and we'll import this into SmartCtrl. But I'll save this first, save as, and we'll go as the FRA. This will be the boost inner analog. Yes, we'll save over, and at the same time we'll do this side and we'll do the digital sweep of this one. So we'll actually just copy and paste this block here, and we'll put it over here, and we'll grab the AC probe as well, and we'll grab this guy, and now I'll disable this one. So this one we're going to do Vsin 2 now, and this is going to be the digital. And to do the digital sweep, I'm going to have to add a 0 to hold. And I'm also going to have to add a delay. We'll slide all this over. So we can put the delay in right there. So this delay is mimicking the digital delay that we're going to see in the digital implementation, and this sample hold is mimicking the sample and hold impact of digitization as well. And we won't sweep nearly as high, although I'll leave it in I'll sweep that high to start with, so we can see what the difference is here. So we'll run this simulation now, and we'll join back when it's done. So here's the digital output. We'll save this and then import this into SmartCtrl as well. So we'll do the S domain and the digital domain implementations sort of at the same time in parallel. So we'll just disable this big circuit now, and we'll come back here and enable this one. Disable, and then I'll pull over SmartCtrl, and let's import some information here. So we'll do a frequency response, current mode control, hit OK. We're doing 17 amps, 50k hertz. We'll grab the analog sweep first, hit OK. We'll grab current sensor, 1 divided by 17. A compensator will be a PI. We'll go from 1 to 0, 19.6 micro. So this is defined in my sawtooth waveform function. And so that's there. And we'll go set now and pick an operating point and see what kind of tuning we can do here. So I think something that we need to be very cognizant of when doing this control design is this brown line is giving us the closed loop response. Is we need this to be close to 0 at around 120 hertz, which is what we're going to be interested in when we do that, because this inner loop has to be able to track the input voltage, which will be a rectified 60 hertz, so at 120. So we do need this to be sort of this phase response to be very flat in that region. So we're going to need something decently quick with not too much phase margin in order to achieve that. So I think something in there will be pretty good. This DC offset in here, we don't need to worry about. It's because we don't have a solution down to 0.1 hertz or close to DC. So this, we won't actually see a step off here. So we'll use these numbers to design our controller. So let me just reduce the size of this and pull it over there. Move that over, and we'll I'll implement the PI control in here, and we'll rejoin the video when I've got that done. Okay, so I've almost got everything wired up here. I'm just putting in the feedback now, and we'll grab a reference. So I've normalized everything so that 1 will be the reference. So we're going to divide the feedback signal here by 17. Let's just make a little bit more room there. And so we'll put a gain of 1/17 there. And these PI values, they're going to come from the KP and KI values from right here. So 2.745 and 16.84 micro. And I'll just put those in. 2.74571 and 16.8413 micro. I've put a limiter block here to limit the duty cycle between some sensible numbers, so a lower limit of 2% and an upper limit of 98%. And this mux is essentially allowing us to run an open loop or closed loop. So with 1 being applied to the bottom, it's going to select the output from the PI loop here. And we'll slide that over to make a little bit more room. So we got 1 there. So now we're ready to run this, and we should see a nice and stable result, and we do. We should check over here, and we should check to make sure V9 is the gating signal, so the output of the comparator. We should make sure that that is not oscillatory. So we do need to make sure that we're gating at 50K and that we're not moving too quickly here. So let's just check this, and we should see that that's switching at 50K, which is great. If our controller was too fast, we might see, high frequency oscillations on the downslope here of the rise of the current, which typically means that the controller is far too fast for the actual carrier waveform. But we're okay in this case, so we're good to go. So now we can have a look to see how good we're doing. So we'll disable this up here, and we'll actually make a little bit of room over here, and we'll enable this. And what we'll do is we'll pipe down this voltage source here. We'll put an absolute value in, abs, and we'll add this down, pipe this down, and multiply this into the reference. Okay, so the gain on this is going to be 1/120, so that's the RMS value. So we're working in RMS throughout. So 120 volts DC RMS is equated to this number here. So this is the peak value to that, and then we're going to divide by 120 on this point, and then that's multiplying into the reference here. So now we can rerun this, and we can look to see how well we're tracking the, and we'll put a voltage probe here as well, V in, and we should be able to see how well we're doing with tracking for the power factor. So let's run this simulation and see how it looks. Okay, so this looks pretty good. Once we're in steady state, we've got a nice looking waveform here. We'll replace this one with V9. We'll put V in here, and we can see that we're tracking, and we've got a really nice looking power factor correction right now. So we'll continue using these values, and that's if we cycle back to SmartCtrl. That's because in this particular instance, we made sure that the phase response was going to be flat out to past 120, out past 120 degrees, or 120 hertz, sorry. So that's why we've got a nice response here. If this was not flat here, we would definitely see some issues with the waveforms. So what we're going to do now is we'll disable that. Actually, we'll disable the entire analog side, and we'll do the digital side now. So we'll bring up SmartCtrl. We'll do another import here. So this is going to be frequency, current mode, OK, 17 amps, 50K. The file is the digital file, open, and we'll go OK. And we'll grab a sensor. It's going to be a current sensor, 1 divided by 17. Hit OK, compensator, PI, and we're going to do 1, 0, and then this is 19.6 micro. And we'll hit OK, set, and now we see that we don't actually get a lot of frequency room now because of the digital implementation and the digital delay. So this is going to cause some problems for us when we try and do the control design. So we can already see that we don't get a nice flat phase response in the digital implementation. So we're going to have to fight for as much as we can get. So I think something bouncing back and forth between stable states. So something maybe so that's what, 22 degrees of phase margin. I think something like that might be is kind of as good as we get. Something down into there. So that's 20 degrees of phase margin. That might be okay. So let's try that for the digital end of things. So we can see how the impact of the digital sampling really kind of impacts things. So let's come back over here, and I'll do the digital implementation over here, and then we'll rejoin the video when I've got that set up. Okay, so I've got the digital implementation almost done. The last thing to do is to load up the coefficients into this PI controller here. So these are S-domain coefficients. This block is actually our digital control block, and what happens with this block is it does backwards Euler in the background, so it converts the S-domain coefficients into the Z-domain. It's also got a built-in limiter, so we don't need to have the limiter like we did on the other end. If I didn't use this block, I'd have to use this S to Z conversion tool to convert my PI controller into with either bilinear or backwards Euler for the proper implementation of the digital coefficients. So this is a really important block. We can't just use the straight regular S-domain block because this does not actually implement a proper digital control. So we need to use the Z-domain PI controller so that this will do the backwards Euler for us, and we're going to take 8846 milli and 97.8 micro and put those in there. So 0.92 milli and 97.8461 micro, 97.8461 micro. The limits are set properly, and we want 50K, not 52K, and we should be ready to go. So I've got the 0 to hold, so current sensor, 0 to hold, to the feedback label. We're doing the gain adjustment, 1/17 again, and our reference of 1, and this one should look pretty good as well. So here's the response from this one. So there's the load voltage, and there is the inductor current, and we can also now pull up the gating signal as well. We just need to make sure that this is also okay, and this also looks nice and stable as well. So these numbers all look pretty good. So what we'll do is we can also now check to see how good we're doing with regards to a PFC implementation. So remember, it's probably not going to look as good as the analog controller, because the phase response wasn't, we couldn't get it quite to unity. So we'll disable that, enable, and we'll put in that sensor again. Okay, so we have the same sensor as before. So we've got 1/120 over the RMS value. We're piping that into the reference here, and then we'll just run it and see what we end up with. It still looks pretty good. Yeah, so this still looks pretty good here, and we'll pull up the output voltage as well. So this is about as good as we will be able to expect with regards to an output ripple voltage. If we want to reduce the size of this ripple, we are going to need to add more bulk capacitance. But if we add more bulk capacitance, that also has an impact on the controllability of this. So we may not be able to do the PFC very well if we have too much output capacitance. There's a lot of factors that we need to really pay attention to when choosing these numbers. So this will probably be good enough for this particular demonstration. So let's go ahead and close some voltage loops. So how we'll do that is what we need to do now is do the exact same thing that we did the first time through, but with regards to the frequency sweep, but this time we're going to do it to the output voltage. So we'll rejoin the video again when I've got the AC sweep set up for the output voltage. Okay, so I've rerun the steady state voltage. So what we need to do is figure out where steady state occurs, and it looks like definitely by 100 milliseconds we're in steady state, and we're going to need that again in the AC sweep block here. So we'll go and we'll put in 100 milliseconds here, and now what we need to do again is so if we start at 1 hertz and go to 20K, definitely we don't need to go this high anymore. I think probably up to 5K is going to be enough. And let's actually, I'll do a couple simulations first to figure out some good parameters. So I like to start 10 to 5K, and then maybe run with 30 points to begin with. And we still need to look at between 5 and 10% of the reference, so the reference being 1. So we want to put in maybe 1 to 0.1 or so. So we'll go with 0.1. And then we also need to put this AC probe out over here on the output voltage. And this is the out, and this is digital. And now everything's set up. So we'll enable this and we'll run the sweep. So when we run the sweep, we'll get a bode plot of the output voltage versus the reference, and we'll use that again with SmartCtrl to design a controller. Okay, so this is my first sweep result. It looks like we need a little bit more amplitude at the higher frequencies, so we can actually come back to the beginning here and maybe actually go to, say, 1.5. And then we'll sweep with a few more points, and we'll go from a lower frequency as well, because we're going to need that in this particular design. And we'll rerun the simulation here. Okay, so here's the next simulation sweep results, and these now look really nice and smooth. And we'll use this with in SmartCtrl to design some controllers. So we'll just save this file. Save as, and this is going to be the FRA, and this is going to be boost digital, and this is the outer. We'll hit save, and we'll go and bring that into SmartCtrl. So with SmartCtrl, we'll ask for a new input. Voltage mode control, we'll hit OK. This time it's 50K. The output voltage is 200. And the file is boost digital outer, open, hit OK, and we'll grab a sensor. We'll do an embedded voltage, an isolated voltage sensor. The reference will be 1, so we recalculate the gain there, and a compensator PI, and these numbers need to be the same as last time. 19.6 micro, hit OK, and now we're ready to go here. So great. So we'll look. So even though it may look like you can have a nice fast controller in here, it's giving you possible solutions out in this range here. This isn't going to work at all because we need to attenuate our fundamental frequency. So we need to have this back here somewhere. Otherwise, we're not going to get a good output response. So we'll do a couple solutions. We'll do a couple solutions with fast controllers, low phase margin, high phase margin, and fast, and we'll kind of look to see what they all look like in the end. So we can see with high phase margin, the slope here is not that steep, so our attenuation isn't as fast as if we have a little less phase margin. So we'll do a couple here and we'll see what the results look like. So we'll do this one to start with. So this is 50 hertz cross with 40 phase margin, and we'll do that over here. So I'll set up the input here. Okay, so I've got it all rearranged so that we're ready to put in these parameters. So for gain, I've got 2.7869, and for time constant, I've got 1.404 milli, and I can blitz these limits away. We don't need them anymore. And again, I'm using the Z domain control block. I've disabled the sweep elements again, and we'll connect this up. I've got my reference set up to be 1, and we're attenuating the output voltage by 1/200 again, and we'll just run it with the DC source so we can have a look at what the waveforms look like. And this looks pretty good. And so now let's run this with the AC source and see what we get. Okay, so now we'll run with the AC input, and we can see that I've got some ripple there, and we can look at the input current here. We can see that it's not perfectly sinusoidal. So let's actually overlay onto this the input voltage. It's been scaled to 1, so we'll just bump it up. I'll multiply it by 25 here so that we can get it overlaid nicely, and so we can do a really good comparison of what it looks like. So yeah, so this is because this downward slope here is because of the speed of the output voltage control loop. So we can play around with it a little bit, and we can really see what the impact is. So let's bring back SmartCtrl, and let's slow things. Let's attenuate even more. So we'll drop down, or actually let's add some phase margin. So relatively the same cross frequency, but with a lot of phase margin now. So let's try those and see what happens. So this is going to be 6.808 and a really big time constant, 24.9586 milli. And let's have a look again at what this does. So again, we can see that it's still not really giving us a good response there. So we really need to go even slower to get a good response. So we really want to be attenuating, those frequencies here. So like 10, 100 hertz, like almost 20 dBs of attenuation. So let's drop this down. So there's a 20 degrees of phase margin, or 50 degrees of phase margin with a cross of 20 hertz. And let's do these numbers again. So 18.9 and 807.805 milli and 2.20796 milli. And we'll rerun, and we should get a nicer looking waveforms now. So there's a really nice looking power factor corrected waveform now. So that's why we can't. So if it looks okay in DC, but the issue is that we need to really like attenuate that 120 hertz signal. So which is what we're seeing on the pink line here. We really need to be attenuating 100, 120 hertz 60 hertz, all those kinds of frequencies. Otherwise, actually 120 hertz, because we're seeing the ripple on the output voltage of 120. So that's going to give us a good response here. So this is a good controller, and we'll do the same thing in the analog domain now. So we'll redo the sweep in the analog domain, and I'll bring in some control on the analog, and we can see what that all looks like as well. If you're interested to know what the power factor is, well, let's just zoom in on a couple cycles here, and we'll hit the power factor button, and we're looking at 0.9978. So I think that's pretty good. Okay, so let's do the analog side of things. Okay, so same as the digital end of things, I've got this all set up now for our AC sweep of the output voltage. So we've got our reference set up. We're running in DC. This is pretty key over here still. We've got the AC probe set up on the output voltage, and again, it's a gain of 1 there. So we need to run it DC to see when steady state is, and looks like 100 milliseconds again is going to be a good look at that. So we'll grab V load. Should be pretty good. So that looks pretty good. So definitely 100 milliseconds. We're good to go. So we'll go back over onto this side, and we'll put in 100 milli here. And then definitely we don't need to go this high. So 10K is probably fast enough. VSign 4 is the name of this source, which is what we need. And then definitely we'll try. On the digital end, we needed a little bit more amplitude, so we'll run with something like this to start with, and see what kind of results we get, and we'll rejoin the video when the sweep is done. Okay, so the sweep is done, and we can see that we've got some nice smooth waveforms. It was good to run the digital one beforehand, and then we'll import this into SmartCtrl. We'll import a new frequency response, voltage mode control. Okay, this is 200, 50K, and over here we'll grab the boost PFC and hit OK. And then we want a voltage sensor again. We want a voltage sensor, so this is the isolated voltage sensor, reference of 1 volt. Okay, and then a compensator, PI, so 1 to 0, and then 19.6 micro. So that all should make sense. Hit OK, OK. And now, again, back to our same issue. We can try to do something really fast, but it's not going to work because we're not attenuating that 120. So we need to come back into one of these regions to attenuate that 120 degrees. So somewhere, like we can maybe push it a little bit out over here. So again, a lot of phase margin, we're not getting a lot of attenuation. If we can really just drop the phase margin down and get some good attenuation there. So something like this, so cross frequency of 57 degrees, phase margin 34, and let's roll with these numbers. Okay, we've got it all set up here, and I'm going to grab the PI values from SmartCtrl and put them into PSIM here. So 2.6 to 789 and 1.0082 milli, and that should be good. So we'll just jump straight to the AC input signal. So we'll run this and see what we get. Okay, so here's the output from this, and I actually don't like the startup here. This does not look very good. So we'll actually come back to SmartCtrl and slow this down a little bit more. I was trying to go a little bit aggressive, but let's go back over here somewhere and use these numbers instead. So that's where's the PI here? So yeah, we're reducing the gain by about half, and we're increasing the integral gain as well. So that probably will give us a better looking look. Yeah, so there we go. So that looks pretty good. So let's lay onto this. We can actually maybe going still a little bit too fast, times 25. Yeah, we may still be going a little bit too fast. We can see here that we could still improve this a little bit. Let's look at the power factor here, 0.9959. We could do a little bit better if we really wanted to. But we can see, again, from that very beginning that the output ripple here, we're never going to be able to do much better than this unless we add some more bulk capacitance in. So this might be good enough. We'll actually look at the input impedance now. So let's set this up to do a sweep of the input impedance for this guy. So I'll set up the input impedance sweep and maybe clean up a little bit of these simulations so it's a little bit more obvious as what's going on, and we'll rejoin the video. Okay, so I've set the boost converter up now to sweep the input impedance. The key thing here, again, we've got our steady state time as 100 milliseconds, and I'm putting in 10% of the amplitude, so it's 120 volts. My sign perturbation is now in series with the input voltage, so Vin and Vin here, and I'm monitoring the input voltage and the input current. So then we'll use Ohm's law to figure out what the input impedance is. So essentially, I've just cleaned up all the other stuff here, but everything else is the same. So we can just run this and look to see what the input impedance is. So when that's done, we subtract the Vin and current. So subtract the current from the input voltage, and this gives us our input impedance in terms of dB, and the phase is here as well. So that's how you do the input impedance for these converters, which you might need to use for an input filter. The output, I've done other videos that deal with doing the output impedance and how to calculate the loop gains, and those should be available online on the YouTube channel or on the website, so have a look at those. To do it for the digital end would be the exact same thing. So we just take this AC sweep and put these probes up and then run it for that. So there we have a PFC from start to finish with average current mode control. So that was 2 kilowatts load, 200 volts DC. Let's run this. Let's have a look quick at the regular simulation so you can see it again. Oh, that's in DC. So let's run it with just the regular simulation again with the AC input so you can see what's going on here. So that was, there's the stabilizing out. We've got the inductor current, looks pretty good. And if we overlay that with our input voltage, then we'll need to boost it up a little bit as well so that we can see it. So we'll multiply by 25, add. And then let's zoom in at steady state. So we'll grab a few cycles here of steady state. And if we do our power factor, we can see that it's 0.9959. So I think that's pretty good. We could try and do maybe a little bit better, sacrifice a little bit of power factor to get a little less ripple up here. But I think that what we've got is pretty good. So if you have any questions or really enjoy these videos, please do let us know. Please check again for more videos. Again, if you subscribe to the channel, you get an update whenever I post one. And you can also contact us for more information. Okay? Thank you so much for watching. That's the end of this tutorial video. And we will hopefully see you again in another video. Thank you so much. Bye now.